Oh, hello everyone. This time we will discuss statistical data, treatment, and evaluation. So take note that we are using statistical data treatment in order to get the correct inference of our results. So there are several most common applications of statistical data treatment and applications, and this is summarized in this slide. So there are six. First is we can determine the numerical interval around the mean set of a replicate result within which the population mean can be expected to lie with a certain probability. So if you can imagine your um, Gaussian curve here, you have your Gaussian curve here. Take note that at the middle of the Gaussian curve, that is the frequency of which the correct data lies. So the interval of which it is still accepted is at somewhat small point of this Gaussian curve. So we will define the confidence interval in order for us to know um, what are the allowable data for the allowable data within our mean. And also, we will determine the number of replicate measurements to ensure the experimental mean falls with a certain range with a given level of probability. So, it is not possible that we will only conduct our study with only one measurement. So, it is best for us to have conclusive result. We have to calculate the number of replicate measurements that we should have in order for us to have more reliable results or data. And also, we can estimate the probability of an experimental mean around the true value, or the experimental means are different. So if you have known value and you have your experimental mean, you can compare it because we can calculate their error. And also, if the two experimental means are different, meaning the data doesn't go along well together. So this can be questioned. And another thing, for us to get a correct data is to determine at a given probability level uh, whether the precision of two sets of measurement differs. So if you have a great difference in the precision, meaning the data that you collected is not acceptable. And next is we can compare means of more than two samples, whether the differences in means are real or a result of random error. So this can be done via analysis of variance. Example, you have a lot of variables that you vary in your data, so you do the analysis of variance in order for you if to know if the results are statistically the same or statistically different. And we can also decide whether to reject or retain a result that appears to be an outlier in a set of replicate measurements. So that is this one summarizes the 6 steps in order to do statistical data treatment. Now let's go to the discussion of confidence interval. So take note that in most quantitative chemical analysis, the true value of the mean cannot be determined because a huge number of measurements would be required. So sometimes our time is just limited, so we cannot really read a lot of um, samples in order for us to give a good result. So in this case, with statistics, we can establish the interval surrounding the experimentally determined mean within which uh, within which the population mean is expected to lie with some degree of probability. So this is known as confidence interval or um, confidence interval. So the limits of the interval are what we call the confidence limit. So example, we might say that it is 99% probable that the true population mean for a set of potassium measurements lies between 7.25, that is the population mean, positive, negative, this one is the standard deviation. So, or the confidence interval. So meaning, out of the mean and this confidence interval, the probability that the mean lies is in between 7.25 plus 0.15, which is equivalent to 7.40. And also, 7.25 negative 0.15 is equivalent to 7.10. So between 7.10 to 7.40% potassium, our data right there is statistically significant. So take note, in confidence interval, we have different degree of confidence level, as you can see in this table. And we also, in each confidence level, we have our Z value or relative frequency. So you can see here that this one is the formula for the confidence interval for the population. You have your data, positive, negative, the relative frequency times the population mean. But mostly we use this confidence interval for our measurements. So this is the mean, positive, negative is equivalent, positive, negative, the Z in your confidence level specified times the population mean over N, which is the number of measurements. So you can see here this table 7.1 summarizes the confidence level and the Z value. So you will use this as the constants depending on the question. And also we can measure the size of the confidence interval as a function of the number of measurements average. Example, these are the number of measurements average. These are the relative size of the confidence interval that we can expect. So what you can see here is the Gaussian curve. So this one shows that the confidence level is the probability that the true mean lies within a certain interval and is often expressed as a percentage. So the blue one right there are our confidence interval. So this one is at 50% confidence interval, meaning the correct mean of data is at this portion, at 80% confidence interval, at 90% confidence interval, 95% and 99% confidence interval. Take note, we cannot really get a 100% correct data, so we can just end up with 99% confidence interval. And you can see there, as our confidence interval increases, meaning the relative frequency of which our data falls into the mean also increases. Okay, so you also have different Z values depending on your confidence interval specified. So this one is an example of the calculation with confidence interval. So determine the 80% and 95% confidence interval. The first entry, 1,108 milligram per liter glucose in example 6.2, and the mean value is around 1,100.3 milligram per liter for the month in the same example. Assume that in each part, the S is equivalent to 19, and this is a good estimate of our population mean. So take note that it is asked that we should calculate it using your what do you call this? 80% and 95% confidence interval. In this confidence interval, you have a given of your Z value, so you can consult that. The formula for your confidence interval, granting that we only have one measurement, is CI is equivalent to mu, positive, negative, your Z value times your population mean or your standard deviation, correct? So in this case, we can calculate the 80% confidence interval in our 1,108 measurement. Our Z value right here is 1.28. Take note that the S is assumed in the problem that is a good estimate of the population. Therefore, our answer is 1,108 positive negative 24.3 milligram per liter. That is the result at 80% confidence interval. So meaning our correct result can lie within that range. But at 95% confidence interval, the result is 1,108 positive negative 37.2 milligram per liter. Now, this one applies if you only have a single set of measurement. Or, this one should be the measurement. This one is CI for your population. So, the measurement, positive, negative, Z times your population. Or your S is a good estimate of the population mean or your mean. Now, In the 80% and 95% confidence interval, in this case, you will be using the formula number 2 for the confidence interval. That is, for mu, is the mean of your data set, positive, negative, the relative frequency, times the population mean, divided by the number of measurements, or n. So in this case, at 80% confidence interval and 95% confidence interval, we will just input the data, which is 1103 at letter B. And then positive, negative, the z value at 80% confidence interval is 1.28, and you have a good estimate of the population, which is equivalent to 19. Since you have 7 measurements according to the given problem, therefore the result at 80% confidence interval is 1100.3, positive, negative, 9.2 milligram per liter. And for 95% confidence interval, you just have to plug in the data. Then you can collect 1100.3, positive, negative, 14.1 milligram per liter. Now, this one is another example for a confidence interval. How many replicate measurements in month 1 are needed to decrease the 95% confidence interval to 1100.3, positive, negative, 10 milligram per glucose? So this one asks our replicate measurements. Take note, in our confidence interval, we have this data. Positive, negative, relative frequency times the population mean over the number of measurement. So in this case, we will get the value of our n. So you have to transpose the data, which are 1100.3, positive, negative, 10 milligram of glucose. You have positive, negative, 10 milligram per liter of glucose. So at 95% confidence interval, we have the z value, which is equivalent to 1.96. Our s value is equivalent to 19. Therefore, take note that our total of this value is equivalent to positive, negative, 10 milligram per liter, as given by this problem. So you just have to input and find the number of measurements. Therefore, in order to get that result, at 95% confidence interval, you have to get a number of measurements which is equivalent to 13.9 or equivalent to 14. Okay, so you just plug the data here. So the z is 1.96. The number of your s, or an estimate of your population, is 19, divided by your number of measurements. Your confidence interval right here is 10 milligram per liter of glucose. We want to find the n. So you have to transpose this data. So it should be 1.96 times 19 divided by 10. And then in order to get the square root, we just have to multiply both sides by, we just have to square both sides in order to get the square root and get the value of n. Therefore, you have to make 14 measurements in order to get that confidence interval. Now, how do we find the confidence interval when our population mean is unknown? So, a single set of replicate measurements must provide not only a mean but also the estimate of precision as earlier. So, S is calculated as the small set of data that may be quite uncertain, and we want the population mean always, because it's always certain because of the number of measurements that it has. So to account for the variability of S, we use the important statistical parameter T, which is defined exactly the same way in this equation, except that S is substituted for our population mean. So take note, if our population mean is not available, then we can calculate here the confidence interval for our population, which is equivalent to mean, positive, negative, the t value, times the s over the square root of n. So we can get the t value for a single measurement. This is your experimental measurement minus mu minus s, or your minus S, or the value for your population mean. Now, if you have n number of measurements, you can use this for the calculation of t. So again, you can use this if you only measure once. This is the value of the t. But if you have a lot of measurements, you can use this instead. Okay? So this one summarizes the different values of t from various level of probability. You can also use this data in order to get the confidence interval using the value of t in case you have only less number of measurements, or you don't have a data for a good population, or you don't have your sigma. Now, this one um, uh, tackles another problem that we can apply the calculation of our T. So a clinical chemist obtained the following data for the alcohol content of sample blood, which is equivalent to 0.084, 0.089, and 0.079. So meaning you have n number of measurements. Calculate the 95% confidence interval from the mean. The three results obtained were only the indication of the precision of the method, and from the previous experience of the 100 samples, we know that the standard deviation of the method is 0.05%. So take note that the standard deviation is a good estimate of your population standard deviation. Sorry, the S is the standard deviation and sigma is the population standard deviation, and the mu is your population mean. So if you would calculate right here the value of your t or the value of your standard deviation, we can get this data. Now, in order for us to get the 95% confidence interval using these measurements, we have to use this formula in which the mean is 0.084, positive, negative. The value of t is 4.30 at 95% confidence interval from the previous table, times the standard deviation, which is 0.0050, divided by the number of measurements, which is equivalent to 3. So this one is the result at 95% confidence interval when you only have your S, which is expected to be a good estimate of your sigma. Now, because t is 0.050%, this one is a good estimate of our sigma. We can use the 95% confidence interval. That is original formula. Again, you use the 95% confidence interval once your S is not a good estimate of your sigma. But if your S is a good estimate of your sigma, therefore you use the original 95% confidence interval and you would get this value. Now let's go to hypothesis testing. So hypothesis testing is the basis for many decisions made in science and engineering. Take note that if we have good hypothesis, therefore our data is acceptable. And that will be tested in order to test the reliability of the data. And take note, there are results of systematic and random errors. So it is useful in order to sharpen the judgment from the experimental results. So in hypothesis testing, we actually have a null hypothesis that assume that the numerical quantity being compared are in fact the same. So we then use the probability distribution to calculate the probability that the observed differences is a result of random errors. Example, if the observed differences is greater than or equal to the differences that would occur in 5 over 100 samples of measurement, or 5 over 100, that is that have a significance level of 0.05. If 1 over 100, the significance level is 0.01. If 10 over 100, that would be 10 over 100. The significance difference is 0.1. So when expressed as a fraction, the significance level, its symbol is alpha, and we can calculate the confidence limit using this equation, which is equivalent to 1 minus alpha times 100. Now, we can actually have the hypothesis testing via the comparison of the following. First is we can compare the mean of the experimental data set with the true value, or we can compare the mean to a predicted cutoff or threshold, or we can compare each other to the mean sets of two or more data. Now, example is we compare the degree of cholesterol that we obtained experimentally with the NIST standard. So we can compare the experimental mean with a known value in here, and we can conduct hypothesis testing. Take note that um, in decision making, in decision making, the hypothesis draw conclusions about the population mean and to the nearness of the known value or your mu naught. So in this case, you can have two hypotheses. Your H naught or your null hypothesis is your population mean equivalent to your known population mean. Alternative hypothesis is that it is abbreviated by the word by the symbol HA. Your population mean is not equivalent to your known value of population mean. Now, in this case, your HE, since your alternative hypothesis, we do not know in which it is greater than or less than, so it is not equal to your known population mean. So that population mean experimentally determined could be greater than or equal to your known population mean, or that population mean experimentally determined could be less than or equal to your known population mean. Next is example is that suppose you are interested in determining whether the concentration of lead in an industrial wastewater discharge exceeds the maximum permissible amount of 0.05 ppm. So what are the hypotheses? Of course, you have your null hypothesis first, that your mu is equivalent to your mu naught, or your population mean is equivalent to your known population mean. So mu is equivalent to your known population mean, which is 0.05. That is your null hypothesis. So since you expect that the discharge of lead in your wastewater exceeds, therefore your population, experimental population, could be greater than that of that known population, or ppm. So that is your alternative hypothesis from the problem. Now, in case that you have lead level is equivalent to 0.02 ppm, and then in this instance, we want to determine if the lead is now different. Therefore, your null hypothesis is that your experimental population mean is equivalent to your known value, which is equivalent to 0.02 ppm. But your alternative hypothesis is that your population mean is not equal to your known value, which is equivalent to 0.02 ppm. Since you are only concerned about the difference, about the difference of your lead level, you don't even infer if even if it exceeds or less than the known level. Now, you can use this criteria in case that you have large sample size. You use your Z value. And in order to calculate Z, you can use this formula. Take note that null hypothesis is equivalent to your population mean minus known value of population mean. And these are actually factors in determining whether we reject our null hypothesis or not. So if your alternative hypothesis, it's a two-tailed test, we do not know if it's higher or lower, your known population mean is not equal to your experimental population mean is not equivalent to your known population mean, you can reject your null hypothesis if your Z calculated from here is greater than or equal to Z critical, or these are the conditions. Your Z critical, you have a table for that. If your null hypothesis is this, you can check if you can reject your null hypothesis if you have this criteria. And if you have alternative hypothesis that your experimental population mean is less than your known population mean, you can reject your null hypothesis if that Z calculated is less than or equivalent to negative z critical. So both of them, since it only determines if it is greater than or less than, it is a one-tailed test. But for this one, we do not know whether it's greater than or less than. We just know that it's different, so it's a two-tailed test. Now, this one is a picture of your two-tailed test for your hypothesis testing. This one is when your alternative hypothesis is the experimental mean is actually less than your known population mean. This one, if your HA of the population is actually alternative hypothesis sa alternative hypothesis na your population mean is greater than your known population mean. That is the graph. This one is a two-tailed test, while this one and this one are one-tailed test. Now, this problem is that you are actually calculating the z from this problem. You can read it and calculate on your own, and then check if it's actually less than at 95% confidence interval. We could actually reject the data or reject the null hypothesis if it's less than or equal to your z critical. So you can calculate this on your own and determine. Now, example, you have small number of sizes. Instead of using z, you use your t value, and you can use this formula in calculating your t. And these are actually the conditions when we reject our null hypothesis out from the calculation. We can actually calculate the bias by getting the difference between the population mean of the bias minus the known population mean. Example, you have two mean sets, and this one, their graph doesn't actually what do you call that, their graph doesn't actually superimpose. So in this case, the difference between them is what we call the bias. So bias actually creates a difference, a big difference in our experimental data. This one, you can check it out and calculate it from your handout. This one actually uses the t statistic or the t result in order to know if ever our null hypothesis is accepted or not. You just have to check the formula and check the conditions. Next is we can compare the two experimental mean. We can get the standard deviation of the mean using this formula, and this one is the formula for the standard difference between the two means, and the standard deviation difference of the means with their number of measurements. And we can also calculate our t when we have our S-pool data from the differences in our standard deviation. But don't worry, this is just shown to you. This is a long process. So if we don't have a known value, therefore we use the differences in the standard deviation between two means. We use this formula. And this one is an example of the calculation. And we also have paired data in which we are using this t value. This one is actually the mean difference. This one is the specific value of the difference to be tested, and the standard deviation difference. This one is the average difference. Standard deviation difference, and this is the square root of your measurement. This one, don't worry too much. We will not calculate on that. We will just actually use that just in case you have paired data, you can use this. And this one is an example of your paired data. So we have errors in hypothesis testing. We have type 1 error if we reject our null hypothesis when it is true. So we call that a false negative. A type 2 error when we accept our null hypothesis when it is false. This one is symbolized by the word beta. So they are inversely proportional to each other. So when you have high type 1 error, you have low type 2 error, and vice versa. Now, we can also compare the variances or the squared of your standard deviation using your f-test. This one is useful when we are comparing the two means or we are using the linear regression analysis. We use the linear regression analysis if we are obtaining the equation of the line and then comparing the two data sets. So you use the f-test in order to determine or statistically treat your data right there. Okay, that's just a short discussion. And then this one are the F values at different confidence level. That it will be just shown to you in order for you to know. That one is an example of the calculation. And we also have analysis of variance. Example, you have a lot of variables. Therefore, for multiple comparisons, you use ANOVA or analysis of variance. So, this one, your null hypothesis is your population mean experimentally is the same with your known population mean. And alternative hypothesis is that there are at least population means that are different. So this one are typical applications of your ANOVA. If you can see, if you can read from this from your handout, they actually test multiple times. So in those kind of testing, you use your ANOVA for your statistical data treatment to know whether your data are the same or they are statistically different. So this one is an example of analysis of variance. And let's go to detection of gross errors. So in gross errors, the main reason why do we have that, because we have outlier. When you have outlier, this is a result that is different from the others in the data set. So it can result to gross error. We can actually remove our outlier via the Q test and the grab test. The Q test, we use the formula Q. We have to get the absolute difference of the questionable data minus the nearest data over the range or the difference between your maximum and minimum value. So example, these are actually your Q critical. We will have to reject if your Q is greater than Q critical. Your Q is the one that you are going to solve and your critical is given depending on your confidence interval. Now, example here, you have this problem, you have these results. So the last one appears to be anomalous according to the problem. Therefore, your questionable data, which is 5.81, should be subtracted in your nearest set of data, which is equivalent to 5.70, it is equivalent to 0.11, divided by the spread or range, which is the difference between the highest value minus your lowest value, that is equivalent to 0.21. So your Q right there is 0.52. We have to check if this outlier, the third one, according to this data, since that is anomalous, at 95% confidence interval, we will reject or we will retain. Take note, when Q is greater than Q critical, we will reject our data. So in this case, this one is less than your Q critical, therefore we have to retain that data. You can calculate your standard deviation including that data. In case that we want to reject that data, therefore the data rejected should be removed from data set and you calculate your standard deviation based on the remaining data. So this one is your Q test. So another test in removing your outlier is your Grubbs test. Your questionable result minus the mean over your S, or which is the value at a certain S, or the standard deviation of the distribution. You can get your G experimental. So when your G value is greater than your G critical, therefore we can remove our data or reject the data. So Grubbs test, your Q test actually is a test for your outliers. So we have 5 summarized statements here in order to detect the gross error. We can re-examine our data if that data is actually preventing the overall data to have a good set of precision. And if we can get the standard deviation differences from from the data set and determine whether that is questionable or outlier, then we test it via Q-test or grab. Or in case that we really want a good data, if we have time and resources, therefore we have to repeat the measurements. And then take note that we will remove the data rejected from your Q-test and your Grubbs test once it is stated from your calculation if your Q is greater than your Q critical. And you calculate your mean and standard deviation from the remaining set of data. Okay, that's it.